properties is a characteristic of matter. Intensive properties, extensive properties, chemical properties, physical properties. There's this, generally speaking, this set of properties that are called colligative properties. And it's so exciting. Do you remember how, well, no, diverting, but do you remember how gases behave the same according to the ideal gas law equation? It doesn't, you don't care what gas it is, whether it's helium, nitrogen, oxygen, carbon dioxide. Well, kind of like that, colligative properties are a characteristic of usually a solute, which is a small amount, interacting with particles with the solvent. And I don't care what the identity of the solute is. That's a colligative property. It does not depend on what it is, but it depends on how much is there, the number of the particles that are there doing the work. I'll show you what I mean. That's a colligative property. So one thing that particles can do is to lower the equilibrium vapor pressure. So vapor pressure lowering, what does that look like? And I'll go ahead and draw so we can kind of start envisioning this. This is my beaker. I'm good at beakers. This is my solvent, and I have added solute. These are my solute particles, okay? Vapor pressure lowering. Well, let's remember what vapor pressure is. I'll go ahead and throw a watch glass over it, okay? And I'll go ahead and choose a different color, a pen. Let's do this way. So this is actually my, and I'll put this down here. The blue are my solute and the black are my solvent. Does that work for you? Because this is black and my solvent. I have actually a certain amount of solvent that's going to go in. I could go ahead and measure this. I could get an equilibrium vapor pressure of that. Well, if we add solute particles, which are blue here, actually it lowers the equilibrium vapor pressure. This is what this is saying. Notice that the blue, these are my solute, and these are my solvent. Okay? One thing about it, it says that that solute should be relatively non-volatile. Well, volatile means that it's going to go ahead and evaporate. Non-volatile means that I'm not going to see any blue particles up here in their gaseous state. It's non-volatile. And that's kind of what we're going to focus on. So let's see. There's a video. I think my videos were. Molecules in their pure state. And this is water. When those big blobs right there, that's a solute, a non-volatile solute. And like the video said, you can kind of think of, they kind of run interference with some of those liquid water to be able to go ahead and evaporate. Okay, so you have some vapor particles up there, but less. Equilibrium vapor pressure lowering with the addition of a solute. And actually, this is why if you look at a macaroni and cheese box instructions, it will say if you are at higher elevations, or maybe this is always, but if you add salt to your water to boil, check this out, that actually lowers equilibrium vapor pressure, and you can jack up the temperature of the water to a higher temperature before it will boil. So adding salt actually kind of, it's a good thing. Okay. All right. So we talked about pressure, temperature, phase diagrams. That's all this is. Pressure, temperature, phase diagram. We have pressure here, temperature here. You can see your Y there. It should give us 3 sectors where we have solid, liquid, and gas. Okay? But you see 2 Y's. You're like, I see double vision. Well, as it turns out, I should get this right. The solid Y, the inner Y, the inner Y is the pure substance, and the outer Y kind of is a substance to which a solute has been added. So, we've been talking about equilibrium vapor pressure lowering. So check this out. If we're at this temperature, this is pure, and this is, I'll go ahead and call it a solution. Right here. Pure solution. The equilibrium vapor pressure has been lowered. All right, so I talked about salt water will boil at a higher temperature. Here we know that when your pressure is equal to the pressure of the atmosphere, and along the pressure units are units of atmospheres. So 1 atmosphere is the normal pressure of works. So up here, this would be the temperature that water would boil if it's pure. This would be the temperature that water would boil. Then colligative properties do depend upon amount. So the boiling point, we're going to call actually elevation. The boiling point elevation does depend upon how much salt, for instance, you've added. It doesn't depend, its colligative property doesn't depend on what salt you added. Of course, we're doing sodium chloride. You could do potassium chloride. I don't know if that's safe, but it's a colligative property. It doesn't matter on the identity of the solute that's been added. Well, when we talked about these diagrams, we said along this transition line between the solid and the liquid, of course, that's when we're going to melt or freeze, right? Notice that when we add particles, and I have a video, I think, to try to show you why this is, but we actually have our freezing point temperature will get, our freezing point temperature will get colder. So the way this is this is the pure, and this is the solution. So it's freezing point lowering. So again, that's why we put salt. And sometimes people are like, a colligative property, it doesn't have to be sodium chloride. It can be potassium chloride. It can be actually dirt. Dirt can run interference and have this.
So is it true that like under a certain temperature, the salt like doesn't work?
Yes, because actually, notice this is where we add salt to make it a lower temperature that freezes, hoping that that it, like if it's 32, it'll freeze, but if we add salt, it might be more like 28 or 20. But there's definitely a limit where it almost causes more harm than good, because you get a little bit of melting that would freeze it, and like, oh crap. Yeah, it only works so good. Yep, exactly. Yeah, I think that liquid is some sort of ionic salt. The word salt isn't necessarily NaCl, but some sort of salt. It could be, some sort of ionic compound in solution, and then it sprays better. So I'll see that too. Yeah. So do you recognize that this is actually, our Y's go down here. We have liquid, gas, and solid. This is actually something we've talked about before. It's a portion of the curve that we've been talking about. We have temperature and pressure here. But this is looking at, again, the equilibrium vapor pressure lowering. The red is pure. The red line is pure, the blue line it's been adulterated. It had some sort of solute added to it, and it's running interference. So you have a lower equilibrium pressure. Oh, I can see the captions now. So the solvent, in large amount, is benzene. Okay, so this is how benzene will behave in its pure state in the cell. The blue line is how benzene will behave if you add some solute to it. So, well, I think I'll just build up to it. But if we go up to the top there, again, the red line is pure, the blue line has a solute added to it. That difference right there, this is that difference in temperature. Actually, that's called the boiling point elevation. That's like how much more it's going to be 5.1 degrees higher to boil. Boiling point elevation. All right. So some convention, anytime you see this knot, remember I call that knot, K-N-O-T. Okay, like we've done knots before. So P knot means actually it's in its pure state. That's convention. We're kind of building up to a few of, some of the equations I gave you, and these will make more sense momentarily, hopefully, with Raoult's law. But P knot means pure, right? Well, then a P without the knot must mean it's the stuff that you had some solute added to it. So it's the equilibrium vapor pressure of the solvent that's in a solution form. So that would be this one right here. You can't see the colors very good, but this was my mixture. I have blue particles running interference. Those are my solute particles. And so this would be my P. And this would be my P naught of my solvent. Okay? Equilibrium vapor pressure lowering. All right. We've done deltas in here. Deltas are always final minus initial. And in this case, the final is the solution you prepared, and the initial is the not one. Okay? So initial conditions would be the pure solvents, the P naught, and the final is going to be your P. So our delta here looks like this. Actually, I'm thinking, reach the blue box. I think this is on the sheet I gave you. I don't see it. Oh yeah, thank you. There it is at the top. Well, kind of. We're getting to the form of it. You're right. It's going to be that, but we're getting there. And I don't know. So this talking about the solvent, because our solute is non-volatile. In case we're going to look at it. So the change in the equilibrium vapor pressure is going to be what it was minus, this one minus this one. Final minus initial. All right. And so, let's see, solvent is less. So these are going to be negative. Does that seem right? This one's less than this one. So we need to quantitate this. How much of an effect we're going to get doesn't depend on what it is. It depends on how many particles you have. So with that said, we can go this route and kind of manipulate that relationship a little bit. We talked in Chem 1, when we got to gas laws, we definitely talked about things are proportional, variables are proportional when it comes to gases. That's what that means, proportional. So that is saying that the equilibrium vapor pressure of the solvent in a solution is proportional to that X means mole fraction. It is proportional, makes sense, to the mole fraction of the solvent in solution, right? So hold that thought. I'm going to take it through a proof to kind of bring you up to another important relationship. So here we go. We know we can take a proportionality symbol and replace it with an equal sign if we also introduce a constant. So here you go. So let's see what that constant might be. Well, if we go ahead and recognize that if the mole fraction of your solvent is 1, then that means you don't have any solutes. Does that make sense? Mole fractions start at 1 and they go down from that, depending on how much solute you have. So if mole fractions is 1, then actually we have a special case where the equilibrium vapor pressure of your solvent in solution will be your pure equilibrium pressure of your solvent. So we go ahead and make some substitutions there. Then that relationship we're getting close to be able to solve for what K is. As it turns out, that variable K is actually the equilibrium vapor pressure of the pure stuff. So do one last thing, substitute P naught, remember that's the pure solvent, back in there, and it looks like this. So you can know that. I cleaned up my slides. I think my surface program rebooted. So. All right. So is this one on there? What's that? Yeah, this last one right here.
What about the top one?
What's that? The top one, the delta P. That we're getting to that. Oh, so hold that thought. Yeah. Okay. So, the mole fraction of the solvent, you can't get any higher than 1. And the more solute you add, this number is going to become smaller, and actually then you're multiplying it by the equilibrium pressure as it was at its pure state. Okay, so that means that the equilibrium pressure of the solution will get smaller. That's Raoult's law. All right, so some key points. You want to get nitty-gritty, it only applies to ideal solutions, and we've talked about ideal solutions where the breaking of bonds and the forming of bonds are similar in characteristics. It would actually, we're not going to do an example where you have a volatile solute, but that would actually kind of confounds things a little bit. Raoult's law would apply to that. And it can work relatively well for non-ideal solutions as long as the solutions aren't too concentrated. Okay. So let's see what this looks like. So say we have A and B, okay, and I think it's going to be A here in a minute. We're going to say A is volatile and B is non-volatile. So what that's describing there is kind of the situation over here on the right that I have, where, well, you can't see it, but I actually have blue and black particles here, only black particles here. Okay, blue, black particles here. So one of the things, yeah, right. One of the things we know about the total pressures is that total pressures are the sum of the individual pressures. So Dalton's law of partial pressures. The total pressure up here is going to be equal to the partial pressure of A plus the partial pressure of B. The next slide says, don't worry about B because we're saying B is non-volatile. What does that mean? It means you're not going to see any of these blue particles up here. They're just going to stay down here and run interference and lower the equilibrium pressure of the black particles. Okay? So let's work a problem. And so actually, these, I think I have these in order. Yeah. So I'll go ahead and try to save some time. These, if you want to put like a 1 here or something, or somehow link this back to your notes, we're going to work this problem. So I'll go ahead and just switch this up a little bit. I'll make this one go away. And what does it say? Calculate the vapor pressure. So we're supposed to come up with this. And actually know that that's going to be a P. Vapor pressure, it's going to be water. I'm not going to put the not because it's a mixture. And it says that the T is equal to 90 degrees Celsius. Oh, 2 sig figs. And it says it was prepared by my solute, my blue dots, or my glucose, 5.00 grams of glucose. And the solvent is water, 100.0 grams of H2O. So that's kind of what we have going on. So we're supposed to come up with the equilibrium pressure of water. And we're going to use Raoult's law that the equilibrium vapor pressure of the water will be equal to the mole fraction of the water, goodness, I can spell, times the equilibrium vapor pressure of the water as it would be if it was pure at 90 degrees Celsius. So that's all we got to do. So this one's going to be the tricky part. It's not really tricky, mole fraction of water. So here are a couple tables, and on this table you're looking at 90 right here. Okay? So that right there, my friends, is going to be P naught. This is the equilibrium pressure of water as pure state. Probably find it here too. So we can use this form of Raoult's law. Okay. We need to come up with the mole fraction of water. How are we going to do that? That's why I gave you the information. Okay. You're going to see on the next slides what I'm going to do is take the mass of the water, the molar mass for water, to come up with moles of H2O, the mass of the solute, glucose, and the molar mass of glucose comes moles of glucose. And then I have to get the mole fraction. This is what I'm going to have to do. So you guys have this slide, right? Did I just give it to you? No? Yeah, you do. Yeah, this is what you have on your sheet. Here. Okay, we go with that. That's like a 10-1 thing. Okay, so we're going to add those two together. They're going to go in the denominator. In the numerator, we're going to put that 5.549. Okay, let's flip it over and see. So the mole fraction of water is pretty high. It should be. You're looking at 0.9950. Then what? That's our x. That's our x, mole fraction. So now all we got to do to finish it up is to go ahead and take that 0.9950 and multiply it by the thing we got in the. This came from the table. That P naught. So one last multiplication. It looks like this. 0.9950 times the 525.8. 4 sig figs. We're looking at a lowered equilibrium vapor pressure of 523.2 millimeters mercury. Okay, so that is this. That's your equilibrium vapor pressure of water to which glucose has been added in those proportions at that temperature. Vapor pressure lowering. So if a follow-up question, I don't think I have this slide for you, but a follow-up question is, well, what was the change? Change is final minus initial, and the final is going to be the solution, the glucose with it, and the initial is going to be the pure stuff. So yeah, I don't have this slide for you guys. So the delta P, the change in equilibrium vapor pressure, is, and this is kind of handy. If you're subtracting or adding, you can put your numbers in parentheses that you're adding or subtracting. Outside the parentheses, put your units. So 523.2 minus 525.8 quantity millimeters mercury. You're looking at a decrease in vapor pressure of 2.6 millimeters mercury. Yeah. Okay. Not bad. Okay, so this is where in my slides I fixed it. We are gonna, you could say it's stop here if you want to, stop here in your notes. This actually is not going to be on the test, and it makes things a little more complicated. If we have a solute that is also volatile, then we have to handle it a little differently. And you guys don't need to know that this semester. The type of semester we've had is. Okay, so let me open up the next part. Here we go. So BPE is affectionately the abbreviation for boiling point elevation, and FPD is the affectionate way of talking about freezing point depression. People. (1001), 1002. Okay. All right. So we kind of looked at this before on our pressure temperature phase diagrams, what this boiling point elevation and the freezing point depression would look like. So just to kind of remind you where those enter, they look like this. Okay. So boiling point elevation, what does that mean? Well, remember the solid line is pure anything, pure solvent. The dotted line is a solution, so a solute has been added. We can kind of see up here at a given pressure, we can see this is atmospheric pressure and temperature boils, or the pressure at which the corresponding temperature is the boiling temperature. You can see this boiling point elevation. Okay. Freezing point depression looks like this, where it's the slide over on this line. It's, of course, the sector between the liquid and the solid. And you see it's this way. So it's freezing point depression with boiling point elevation. So this is kind of a repeat slide. We're going to kind of quantitate this a little bit. Now, I'll show you where this fits in, and we're kind of building up to another few of those equations. You have to be careful with the subscripts. This is not the mole fraction of the solvent. This is the mole fraction of the solute that's in lesser amount. So make sure you know which mole fraction you're talking about. This is showing you kind of how if you have here pure solvents, you get these nice freezing solidification up there, and where it actually has the solvent has a solute added to it. Your freezing is blobby. So how does the solidification work with kind of interfering particles? Well, this would be pure stuff, and this would be not pure stuff. So again, now we have our solute particles kind of going interference with our solvent particles solidifying. And it lowers the temperature that needs to exist in order for solidification to happen. So freezing point depression. It's not as obvious, I don't think, as the boiling point elevation to me. So this was one form of Raoult's law where the equilibrium vapor pressure of the solvent, when it's got its solute added to it, is equal to the mole fraction of the solvent times the equilibrium vapor pressure of the solvent if it was pure. This is, we're going to kind of develop another form of this. Well, what if we know we just have two things added together? So the mole fraction of those two things added together should be equal to 1. So the mole fraction of the solvent plus the mole fraction of the solute will equal 1. Well, we can go ahead and rearrange that, solving for the mole fraction of the solvent, and then take this quantity and substitute it back up in for the mole fraction of the solvent. And this is what it ends up looking like, where we have equilibrium pressure of the solvent to which a solute has been added is equal to quantity 1 minus the mole fraction of the solute times the times the pressure of the solvent in its pure state. And we can take this this P naught and distribute it through this quantity, and it looks like this. And we can do a little bit of changing around. I think I'm going to move that over. Oops, sorry. Yeah. We'll go ahead and move the P naught of the solvent over. There'll be subtraction over there. I'll use this over there. Of course, what this is your delta P, your equilibrium vapor pressure. The change in equilibrium vapor pressure. So now we have another form. And this is actually the form that you see there, and it can be helpful too. But keep your wits about you. Notice that the subscripts here. This is saying that your equilibrium vapor pressure lowering will be equal to negative mole fraction of your solute times the pressure of your solvent in its pure state. Okay, another form of Raoult's law. Well, we need to quantitate these boiling point elevations and freezing points depressions. Are these on there? So you just need to know how to use this. Sometimes I'll chant it to myself. Boiling point elevation, freezing point depression. Boiling point elevation, freezing point depression. So what this means, what this says is how much it's going to be elevated is equal to K, and you have to look this up. So this K BP, that's specific for the solvent. KBP, that's actually what we call the boiling point elevation constant. I'll give that to you. Well, I might or I might not. And then little m, do you guys know what little m's are? Molality. Molalities, yes. The molality of the solute. Look at the property, I don't know what it is, but I need to know how many particles there are. I need to know specifically its molality. And I'll warn you ahead of time, the signs, the plus and minus, they kind of drive me nuts. I have a slide to kind of show you and hopefully guide you some more information. Of course, the two vertical lines being the absolute value of. So the absolute value of the freezing point, but this section is we're going to depress the freezing point temperatures. Remember when we add solute. Freezing point, depression constant times molality and solute. For the delta T's, it's always final minus initial. The final, and remember these knots go along with how the knots do with pressure. This means the temperature in its pure state. This means the temperature when it's in the solution. Okay, so those knots are here to stay. They kind of go. So the way this works, boiling point elevation, your delta T will be positive, freezing point depression, your change in freezing point temperatures will actually be negative. There's your working problems, homework problems, or problems on the test. You just kind of have to remember boiling point elevation, freezing point depression. Okay. So those big K FP, big K VP, okay, those are the constants associated with a particular, there's too many S's, associated with the solvent, the thing that is there in greater amounts. So you should have a couple slides with some freezing point depression, boiling point elevation. Okay. The C, this is the degrees Celsius per molal. That's what the CM to the -1 is. That's the units of both constants. The boiling point elevation constant, the freezing point depression constant, is degrees Celsius. This is degrees Celsius. Okay. Yeah, there's not a degree there, but there should be a degree there. And this K sub B is equal to the same thing as K BP, same thing. All right. But check out this last one. We talked the other day where molal is equal to moles of solute per kilogram of solvent. So with that in mind, that's where this comes from. Degrees Celsius per molal, it's the same thing as degrees Celsius times kilogram of solvent divided by moles of solute, because molal is in the denominator. So you have to flip it. So here's some more information. Again, the freezing point depressions and the constants and the boiling point elevation constants are specific for the solvent. Solute, colligative. I don't care what it is. I just need to know the molality of the solute to know what effect it's going to have on the freezing point and the boiling point. All about molality. So this is the whole sign convention. It kind of drives me nuts because I think as I've been teaching this over the years, I've probably kind of done different things. But you're just going to have to remember that the freezing points will be lower, the boiling points will be higher of your T's. All right, so let's work a problem. I have printed this one for you too. This one. So, now there's totally not enough information for this. Let's see. Erase this. So we have some benzene, and it is freezing. Must be freezing lower than it should because it's actually. Wait, what's the freezing point? Oh, I know. That's right. On the next slide, you can see that benzene will actually boil at a lower temperature than 82. So I was trying to think how. So we have benzene, and here is my solute. Okay, and it's boiling. boiling. So T, in which it boils, is 82.0 degrees Celsius. Notice I did not put the knot there, okay? Because this is a solution. And I got something wrong with that. So I want to know, question mark, what temperature will it freeze at? I have no idea. Well, here's kind of the strategy. Well, to know this, actually, to do this, our T knot, you see why this is T naught? Because we looked it up on the table. Normal boiling point temperature is 80.1 degrees Celsius. We can go ahead and get our delta T from that. And then once we have our delta T, we can go ahead and plug that into this one right here. Once we have our delta T, and we have the boiling point elevation constant of benzene, I can get the molality of the solute. Once I have the molality of the solute, I can turn to freezing now and go ahead and apply a freezing point depression to it. Okay, so yeah, you will in this case need to know the boiling point elevation constant for benzene is 2.53 degrees Celsius per mole of solute. We'll also need to know the freezing point depression constant for benzene is 5.12 degrees Celsius for every mole of solute. So again, what are we going to do? We're going to see what sort of elevation we have due to the presence of a solute to get to the molality of the solute. Once we know the molality of the solute, we can go ahead and get the freezing point depression. We can apply that delta T FP to get to what its new freezing point temperature will be. What's it? You got it? You answered your own question?
No.
Okay.
I was wondering,
Boiling point elevation? Yeah, yep. Chant it. All right, so let's see. We're going to start with this one, actually, sort of. We're going to use these two to get the delta T BP. So it's final minus initial. So it's this one, 82.0 minus 80.1. So you guys should have these. So your delta T BP, you're looking at 1.9 degrees Celsius. So do you see once we have delta T BP, we already have K BP, so we can go ahead and knock out molality. If we rearrange that top equation, the molality of the solute will be the change in boiling point, the delta T BP, divided by the K BP. So we can kind of plug in what we came up with our delta T BP and divide by our K BP. Notice we have to make sure our units come along. So here our units of degrees Celsius cancel. The degrees Celsius, the numerator of the numerator, and the numerator of the denominator, they cancel. And we've done this before where you end up with the inverse of molality in the denominator, and that is equal to molal. It's magic. 2 sig figs, you're looking at a molality at 0.75 molal. So we're not quite done yet. Now we need to switch gears. Instead of boiling, we're going to freeze. So we're going to apply that then to the freezing point. So our delta T FP looks like this, and we were given the freezing point depression constant of 5.12 molal, or excuse me, degrees Celsius per molal times our 0.75 molal. 2 sig figs, and again, this is where we have the absolute value thing coming along. The absolute value for the change in the freezing point temperature will be 3.8 degrees Celsius. So again, we have to keep our wits about us. So to come up with the new freezing point temperature, we have to take the original freezing point temperature and take that off of the reason for the depression, right? So the new freezing point temperature we can calculate by taking what it would remember the freezing point was given. 5.5 degrees Celsius. We have our depression of 3.8 degrees. So round to 1 decimal, you're looking at 1.7 degrees Celsius will be the new depressed temperature it will freeze at. Pulling out all the stops. They're fun. It was given. Yep, it was the T0 freezing point. Yep. They're fun. All right. More problem. And I've done this before. Now, this is a 2-pager. Classic. If I've done this before, I mean, sometimes I feel like it's change her up a little bit. Okay. So this is where sometimes you might want to abbreviate things. So I have a solution, solution of 5.0 grams of lauryl alcohol in 0.100 kilograms of benzene. So here's the deal. When I read it a few times, I'm like, oh, okay, lauryl alcohol. Like I might even abbreviate that is equal to LA, lauryl alcohol. Down here, I have my benzene, and I might even, abbreviate it. So benzene is my solvent, lauryl alcohol is my solute. All right, so what do we got here? Looks like we got 5.00 grams of my solute is added. Down here, I've got a mass of 0.100 kilograms of solvents. Solute. All right. What is the molar mass? Oh, wait. What else is it? It says it freezes at 4 degrees. So that's my T, right? Because it's not my pure, it's my mixture. My freezing point of my mixture is 4.1 degrees Celsius, which must be lower than it would have usually frozen at. Freezing point depression, all that. So, question mark, molar mass of lauryl alcohol. Well, if you don't know where to begin, start by comparing these two and come up with a delta T, FP, and then know that that's your KFP times the molality of your solute. That's basically what we're gonna do. So we have to be given the freezing point depression in this problem. Freezing point depression constant for benzene. We also need to know what it would freeze at normally for this problem. And we can look both of those up. So those are both given. So let's see. Normal freezing point temperature, we're looking at 5.53 degrees Celsius. Freezing point depression constant is 5.12 degrees Celsius per mol. Solute. Again, remember freezing point depression constants, boiling point elevation constants are dependent only upon the solvent. All right, here we go. So is this where the slides I gave you? No? Yeah. All the slides I gave you. So if we recognize that depression that we're seeing, here we go. This is the new depression that we're seeing can be quantitated this way. We can rearrange that to knock out molality, and it looks like this. So the molality of the lauryl alcohol, which is going to help us get to the molecular weight of lauryl alcohol, is the delta FP over KFP. Delta FP, the absolute value of, looks like this. It's the new temperature it froze at minus the old temperature, or what it frozen at, and if it's pure, you're looking at delta T FP of 1.4 degrees Celsius. We plug it in then, 1.4 degrees Celsius over the KFP, 5.12 degrees Celsius per molal. Again, that's going to give you units of molal. You're looking at a molality of this ratio, mass of lauryl alcohol to benzene of 0.27 molal. You'd be like, well, how does that get me to the molar mass? Well, if we remember what molal is by definition is unpacked here. Molal by definition, it means that we have 0.27 moles of lauryl alcohol per 1 kilogram of solvent, which in this case is benzene, right? Sorry. Well, we're going to use that definition, unpacking Malau, along with, I need a different color, along with this information about the original problem, the relative amounts of lauryl alcohol and benzene, to get down the road. There's different ways to skin this cat. But if we go back to the original information, we knew in this case we had 1 kilogram of benzene, 0.1 kilograms of benzene. Here's the molality. Okay, do you see where this will get us moles? See how the back label works there? This will get us moles of lauryl alcohol, La, that we had. And then what is molar mass? Well, molar mass is grams per mole. So once we have moles, yes, I saw that like what? Once we have moles, then all we got to do is divide that by, or take 5 grams divided by that moles. Okay, so you're looking at 0.027 moles. And so again, the original problem said we're looking at 5 grams. That's equal to 0.027 moles. We can get molar mass just grams per mole. 2 sig figs, you're looking at a molar mass of 180 grams per mole. So,